All right, so transformation between balanced sources. So let's start with a Y-connected voltage source, right? It's whatever day it says on the syllabus. I think that's Monday. So here's our A phase terminal, our B phase terminal. Down here, let's do our C phase terminal. Neutral in the middle. Like so. And let's say that this will be voltage VAN, VBN, and VCN, like so. Voltage VAN will have a value of VP RMS with a phase angle of 0 degrees. VBN will be VP RMS with a phase angle of negative 120 degrees. Make sure that looks like a 20. And VCN is VP RMS with an angle of negative 240 degrees. Well, we have already established that the line voltage VAB, and I'll draw it up here, can be determined by writing a Kirchhoff's voltage law equation around that top triangular loop. This guy right here. And what we'll find is that VAB is equal to VAN minus VBN, which is the same as VAN minus VAN times one angle negative 120 degrees, which just comes out to VAN times root 3 angle 30 degrees. And continuing on with this, we could say that VBC is just VBN root 3 angle 30 degrees, and VCA is just VCN root 3 angle 30 degrees. Okay. So we now have both our phase voltages and our line voltages, and we understand that there's a relationship between those two quantities. So my question to you all is as such. If I were to connect a delta connected load to my Y connected source, would it be able to tell the difference between a Y connected voltage source and a delta connected voltage source? So let me draw a picture what I mean here, right? So here's VAN, BN, and CN. Assuming my transmission line impedance is negligible, I could connect a load across my terminals like so. Here would be B and B and C and C. So the voltage seen by that delta connected load would be our line to line voltages, right? So the voltage drop across the A phase of my delta connected load would be this voltage VAB. The voltage seen by the load across the B phase of the load would be the line voltage VBC, and the voltage across the C phase of the load would be VCA. My load is in no way, shape, or form connected to the neutral terminal. It does not know the neutral terminal exists because it is not an intelligent thing. It is just an impedance. So, can my load tell that that source is Y connected? Not at all, right? It does not matter whatsoever. As long as it's supplying the correct voltage, it's going to behave correctly. So what we've accidentally stumbled into here is how to convert a Y connected source into a delta connected source. And it's just multiply our phase voltages by √3 angle 30 degrees to give us effectively our phase and line voltages for our delta connected source, okay? So we found that to go from this representation A, B, and C to this representation, so those should definitely be on the other side. Sorry, let me scooch this over. A, B, C, B, B, C, like so. So to go from Y to delta, we need to multiply by √3. Dang it, I'm just writing garbage today. Angle 30 degrees. So I'm going to ask you guys a very important question here. If we know how to convert from a Y to delta, how do you think we're going to convert from delta to Y? Divide by √3 angle 30. Oh my gosh, the math is so incredibly difficult. I'm going to choose to represent that as multiplication by 1 over √3 angle negative 30 degrees, just so that it looks like multiplication in both directions. But it is dividing by √3 angle positive 30 degrees, okay? So we now know how to transform between balanced sources, yes. So to go from Y to delta, yes. To go from delta to Y, we simply divide by √3 angle 30, or multiply by 1 over √3 angle negative 30, which is the exact same thing. So like I had said previously, we already kind of knew this because we used it in some example problems last week. Yes, Isaiah, how may I help you?
Go back up where you're like, what is that?
RMS.
Oh.
Yep. Yes.
So whenever you're approached with a problem that has one source and one load, they're different. it's better to change the source instead of the load.
We're going to talk about how to change loads in a second. So the goal here is to be able to convert anything into a YY circuit, because a YY circuit means we get to use that incredibly trivial equivalent electrical circuit that was just a source in series with two impedances, which effectively a child should be able to understand. Yes, Toby.
Reason you want to go to Delta?
So if we had an unbalanced system, delta, let me draw some things out here. This is a tangentially related thing, right? So you don't need to write any of this down. This is going to be quick and sloppy because I just want to look at something here. So if we had a YY connected three-phase circuit, where we had an unbalanced system and a neutral conductor available, it's looking like I would have three mesh equations to deal with in order to analyze that. Now, if instead my source were delta connected, and my load were Y connected, I have three loops, so still just as easy. If I were to go, and obviously if it were delta connected source and Y connected load, it would still be the exact same effective configuration. If I go delta delta, I wind up having four loops. However, in this loop, so I'm just going to call this my source loop. We know that all those voltage drops add together to make zero, which means that loop doesn't really do anything. And we're still going to wind up with a three loop system to solve. Excuse me. For whatever reason, it's not intuitively obvious to me. Typically, when you're looking at an unbalanced system, working with a delta delta seems to be the easiest way to set up all of your relationships. And that's purely from an analytical standpoint. From a practical standpoint, it's actually much more likely that you'll have a neutral conductor in that system. And the reason being is that having a neutral conductor there means that the imbalance won't be carried by any of your phase conductors, which means you don't have to size them any larger than they would normally be. Because all of the imbalance will wind up flowing up and down the neutral conductor. And as long as it's not hugely imbalanced, you get to use a smaller gauge of wire for your neutral conductor, which is cheaper. Trying to think of cost perspective or anything else. The number of conductors is, it's either going to be 3 transmission lines if it's any delta connection, and at most 4 transmission lines, including the neutral conductor, if it's a fully Y-connected system. So off the top of my head right now, I can't think of any real reason why you might prefer one over the other, except that you get larger voltages in a delta connection than you do in a Y connection, which means on the flip side of that, because the power is going to be the same either way, you're dealing with smaller currents in a delta connection and larger currents in a Y connection. So I think those would typically be the limiting factors on the ratings for whatever you're trying to hook up. All right, so just a bunch of shitty drawings there. Back to the topic at hand. So we have figured out how to transform sources. That's very easy. Now we're going to talk about transforming between balance loads. And I am going to formally introduce here the delta Y conversion that I mentioned briefly in the first homework assignment that I ever assigned in this class, where I asked you guys to calculate the Thevenin equivalent impedance of a particular network directly, that required you to use the ratio of, I think, VThev to I Norton, because if you didn't do that, then you needed to know how to do this, which nothing wrong with giving it a Google, but let's talk about it in more detail here. Okay. So on the left-hand side, I'm going to put a Y impedance. So something like this. And for the sake of argument, let's say that not all of these are the same impedance just yet. So that this guy here would be an impedance ZYA, this guy here would be an impedance ZYB, and this guy here would be an impedance ZYC, and we have a neutral conductor there in the middle. Then over here on this side, I'm going to put a delta connected load, putting the terminals in the exact same place. So this will be Z delta A. This guy over here is Z delta C. And this guy over here would be Z delta B. So if I look for the impedance seen between terminals A and B of my Y-connected network, what do I see? What is the equivalent impedance seen looking into terminals A and B of this network? So if I'm looking in through terminals A and B, what do I see? ZYA plus ZYB, that's it. And similarly, between B and C, I would see ZYB plus ZYC. And between C and A, I would see ZYC plus ZYA. Now, on this other side, if I look in between terminals A and B, what do I see? Just Z delta A between A and B. Close, but not quite right. Yeah. So Z delta A in parallel with the series combination of Z delta B and Z delta C, okay? So Z delta A times Z delta B plus Z delta C over Z delta A plus Z delta B plus Z delta C. And I can repeat that for the other two impedances as well. So that would be Z delta B sorry, that should be A and B. All right, so we're trying to figure out a transformation between these two forms. So effectively, what we have here is a three equation, three unknown system. Let me explain what I mean by that. If we know what our Y connected impedances are, so that ZYA, ZYB, and ZYC are known, we can set the impedance seen between terminals A and B of both networks to be equal and solve for the delta connected impedances. Or if we know what our delta connected impedances are, we can set the impedances seen between each set of terminals equal to each other and solve for the unknown quantities, which would be the Y connected impedance. A few years back, I used to make you guys do this by hand as a homework assignment, and the students overwhelmingly hated it because it was just 6 tons of algebra with no real purpose other than doing a whole shitload of algebra. So instead of doing that, we are just going to skip ahead to the results, okay? So for a Y to delta transformation, what we're going to wind up having, and let me put in parentheses here. So this means ZYA, ZYB, ZYC are known. We wind up getting Z delta A is equal to ZYA times ZYB plus ZYB times ZYC plus ZYC times ZYA, all divided by ZYA. Z delta B is going to be the exact same numerator. Divided by ZYB. And Z delta C is going to be the exact same numerator, this time just divided by ZYC. So now let's talk about if we have a balanced system. In a balanced system, ZYA, ZYB, and ZYC would all be equal to each other. So if I just plugged ZY in for everywhere I see ZYA, ZYB, or ZYC, I would get 3 ZY squared over ZY, or 3 ZY. So to go from a Y-connected impedance, balanced impedance, to a delta-connected impedance, I simply multiply the impedance values by a factor of 3. This only works if it's balanced. If it's unbalanced, we have to use this big ungodly equation. Okay. Going the other way around, much to no one's surprise, hopefully, we're going to divide by 3. Sorry, what? Mhm. So for a delta Y transformation, where Z delta A, Z delta B, and Z delta C, that looks too much like an A for my taste, are known, we wind up getting the relationships ZYA is Z delta A times Z delta C divided by Z delta A plus Z delta B plus Z delta C. ZYB is Z delta A, Z delta B divided by Z delta A plus Z delta B plus Z delta C. And lastly, ZYC looks like Z delta B times Z delta C over Z delta A plus Z delta B plus Z delta C. For a balanced system, we would have ZY is equal to, and now if we look at this thing, it's going to look like Z delta squared over 3 Z delta, or simply 1/3 of Z delta. So for impedances, to go from Y to delta, we multiply by a factor of 3, and to go from delta to Y, we divide by a factor of 3. And now we have enough information to convert any combination. So Y delta, delta delta, delta Y into a Y circuit and do our analysis. So let's look at something difficult. I want to use a new page, so I'm waiting for people to stop writing. All right. So I don't remember if this is exactly one of your homework problems or it's just very similar, but either way, it's okay. I want us to analyze the following circuit, okay? So this is going to be large and gross, at least in appearance, but it won't be all that bad in practice. So here, I'm going to have a Y-connected source. A, B, C. I have my transmission line impedances, ZW, ZW, and ZW. And on my load side, I'm going to have something real gross. I'm going to connect a delta connected impedance in parallel with a Y connected impedance. So I'm going to start with my delta connected impedance because I want to make sure we're all on the same page here. So I have some impedance Z delta connected between the A and B transmission line terminals. I have some impedance Z delta connected between the B and C transmission line terminals. And I have some impedance Z delta connected between the C and A transmission line terminals. So just checking in with you guys, does my delta connected load look connected correctly? Okay. Now I'm going to connect my Y connected load. So I'm going to put a neutral here. Between B and neutral, I will have some impedance ZY. Between A and neutral, I will have some impedance ZY. And between C and neutral, I will have some impedance CY. Is my Y connected load connected correctly? Absolutely. This is as hard as I can possibly make a circuit for you to analyze. Because if I gave you two Y connected loads, you could just lump them together. If I gave you two delta connected loads, you could just lump them together, right? So the hardest thing that I could ever possibly give you is a Y connection and a delta connection at the same time. What I want us to find are the following quantities. I want our line currents. But I also want our phase currents. In our load. So here are all of my delta connected phase currents. And here are all of my Y connected phase currents. Now, realistically, we're only going to actually calculate the A phase of this because we know at this point that we can just shift everything by 120 degrees to get all of our other phases. And I don't feel great, so I don't want to do a bunch of unnecessary math. Okay. So let me specify a few things for you all. Let's say that the voltage VAN is 120 angle 20 degrees volts RMS. Our transmission line impedance is 0.1 plus J 0.08 ohms. Our Y connected impedance is 8 plus J 2 ohms. And our delta connected impedance per phase is 12 plus J3 ohms. Yeah, that'll be fine. 0.1 plus J 0.08.
0.8.
Yes. All right, so we are going to use our single phase equivalent circuit to figure out as much as we can, and then we're going to wind up coming back to this original circuit diagram to figure out everything else. That's going to be our methodology for literally any non-YY system or anything that we can't find with just our single phase equivalent circuit, right? So as it stands right now, we can't actually draw a single phase equivalent circuit just yet because we have that delta connected impedance that's messing with us. So instead, we are going to have to figure out what its equivalent Y connection would look like. So I'm going to say that we're going to have some impedance that I'm going to call Z delta Y. And this is just our delta connected impedance transformed into a Y impedance. So how do I get a Y impedance from my delta? Yep, so just divide by 3. So 12 plus J3 over 3 looks like 4 plus J1 ohms. Nothing wild or crazy, chose numbers that the math will work out nice and neat with. So from here, our single phase equivalent circuit is going to look something like this. So here's 120 angle 20 degrees, volts RMS, lowercase a, lowercase n. Here's ZW, capital A, screen scrolled on me, capital N. Here's ZY. Here's Z delta Y. I'm now going to draw on this diagram what we can find. So we can definitely find our line current IAA because that's a direct thing. We can definitely find our, excuse me, I'm using the wrong color here, our phase current through the Y connected load, IAN. And that's it. We cannot find our phase current through our delta connected load because we no longer have a delta connection to look at, right? So we're going to have to do something else to figure that out. And there are a couple of different ways that we can approach that. We'll get to that in a couple of minutes. So I'm going to throw it to you guys. How would we find either of these two quantities that I have indicated on the diagram that are actually stuff that we're looking for? Anybody have any thoughts? Mm-hmm.
Your voltage over the wiring
Mm-hmm.
plus the do the two Y impedances in parallel, or do you just do the?
So it would be the two Y impedances in parallel because that's what the line current is going to see, is effectively those two impedances in parallel. Absolutely right. So we would have IAA would be equal to 120 angle 20 degrees volts RMS divided by 0.1 plus J 0.08. And then over here, this is going to look like 8 plus J2 times 4 plus J1 over 12 plus J3. And this comes out to be 41.875 with an angle of 4.897 degrees amps RMS. Yes. 3, because 2 plus 1 is 3. Yep. Nope, that is a 3. J 3 ohms. Anybody have any questions, comments, or concerns about how we determined our line current using our single phase equivalent circuit? Move my big head out of the way for Toby.
Why are we not able to find the delta?
There is no delta connected impedance anymore. Right, so we could find the current flowing through the placeholder, but the placeholder isn't delta connected, so why would we be able to get a delta connected current?
It's because we converted the delta to a 1.
Yeah, so I'm looking for the current that's flowing from transmission line terminal A to transmission line terminal B. There is no current that flows directly from transmission line terminal A to transmission line terminal B in my single phase equivalent circuit because there is no transmission line terminal B in my single phase equivalent circuit at all. So I can't solve for it directly. It does not exist there. Right? Is there a transmission line terminal B literally anywhere in this circuit? No. So that makes it significantly harder to solve for that current. All right, so any other questions before we move on to the next bit here? All right, so how would we solve for our phase current through our Y-connected impedance? Current division, absolutely. So the current IAN would just look like IAA times 1 over ZY over 1 over ZY plus 1 over Z delta Y. Which is going to look like 41.875 angle 4.897 degrees amps RMS times 4 plus J1 over 4 plus J1 plus 8 plus J2. And this is going to come out to be 13.958 with an angle of 4.897 degrees amps RMS. Just as a quick thing here, because it's not super obvious what I did, this is the same as IAA times Z delta over Z delta Y plus ZY, which is how current division can be written when there's exactly 2 impedances in parallel, which is the case that we have. Walker.
So is this small circuit just like fast transfer to help analyze the big circuit?
Yes, this is representing a portion of the big circuit.
That's why we can't.
Yeah. Yep. Absolutely right. Okay. Okay, so we have these 2 currents. So now let's revisit how we might solve for the current IAB. And there are two different ways. I'm interested in hearing what you guys think. So we're trying to solve for this current right here. And there are two different ways to do it. Neither of them particularly difficult. Caro, how might you?
Compensate some current. We don't have time.
It absolutely does, but we don't need ICA. Well, let me prove that to you. Okay. So Caro has suggested that we apply Kirchhoff's current law at the transmission line terminal A in order to solve for the quantity IAB. He says that we need to know ICA. He is correct, but also incorrect, and I'll explain what I mean by that. Okay. So I'm going to set this up as currents flowing in equals currents flowing out, right? So that would mean that I would have a current IAA, which is a known quantity flowing in, plus a current ICA, which is an unknown quantity flowing in, is equal to IAB, an unknown quantity flowing out, plus IAN, which at this point is a known quantity flowing out. Anything wrong with my KCL equation? Want to scroll back up so we can see it, make sure everything's on the up and up. Currents flowing in equal currents flowing out. That's KCL all day long, right? Okay. So now let's talk about why. Actually, let me rearrange this and then we'll talk about why I don't actually need to know what ICA is. Okay. So I'm going to move all my known quantities to the left and my unknown quantities to the right. So that's going to look like IAA minus IAN is equal to IAB minus ICA. Now, the reason why I don't need to know ICA explicitly is because I have a balanced three-phase system, and I know that ICA and IAB are related to each other. So I could instead express the right-hand side as IAB minus IAB times what? One angle negative 240. Absolutely right. So the B phase lags the A phase by 120 degrees. The C phase lags the B phase by 120 degrees. Combine those together and we get a negative 240 degree phase angle difference between the A phase and the C phase. So what is 1 minus 1 angle negative 240 degrees? Root 3 angle negative 30. So now we have a single thing to solve for, right? So rearranging this, we could say that IAB is equal to IAA minus IAN divided by root 3 angle negative 30 degrees. Substituting in our results, we wind up getting 16.118 with an angle of positive 34.897 degrees amps RMS. That is one way to do it. That is the correct answer. However, I believe that there's a slightly easier way. So let me talk about that slightly easier way, in my opinion. Let me do this in this gray color. So we found the current IAN already. I believe that that gives us enough information to find this voltage VAN. And knowing this voltage VAN, we should then be able to just do a transformation to find this voltage VAB, and VAB divided by Z delta will give us the current IAB. So let's prove that we get the same answer. So VAN is just going to be IAN times ZY, 13.958, with an angle of 4.897 degrees. Amps times 8 plus J2 ohms comes out to be 115.104 angle 18.933 degrees volts RMS. The voltage VAB should just be VAN times √3 angle 30 degrees. So I have this written out, but somebody that borrowed my notes when they taught the class last year wrote a different number down. So I want to make sure that I'm right there wrong because I'm me. Yeah, a little bit of rounding error, but that's all fine. Times √3 angle 30. Yep, she's wrong. 199.366 with an angle of 48.933 degrees volts RMS. IAB would just be VAB over Z delta. So that's 199.366 angle 48.933 degrees volts RMS over, if I'm not mistaken, 12 plus J3 ohms. And I got 16.117, that's just rounding error, so 118, angle 34.897 degrees, excuse me, amps RMS. Both ways equally valid to get the exact same result. Just depends on whether you want to go through the trouble of writing a KCL equation or you want to be as lazy as I do and just use transformations because that's what they're for. Nothing wrong with either approach. And obviously both of them gave us the same answer. Yes, sir. So let's say that I have Y connected impedance. Here's A, B, and C. This is the voltage VAN. This is the voltage VBN. This is the voltage VAB. You don't need literally any numbers at all, really, right? So I can see by writing a Kirchhoff's voltage law equation that VAB is just equal to VAN minus VBN, which is VAN minus VAN times 1 angle negative 120 degrees. Isaiah, do me a solid and tell me what 1 minus 1 angle negative 120 degrees is. Yep. You can put it in your calculator if you want to verify that. So now I have this voltage VAB. Because the delta connected impedance is in parallel, it has the same voltage drop over it. And then I can use Ohm's law to find the current that I was looking for. No problem. I'm not trying to be any more of an asshole than usual, just to be clear here. To me, at least when I was first learning this stuff, it seems intimidating because there's so much stuff going on, but it's all based on simple relationships. So it can be difficult to come to grips with the fact that it's not as hard as it looks like it's supposed to be. I think is one of the biggest things that students struggle with. But fundamentally, you can always go back to KVL and KCL relationships to figure all of this stuff out. So anyway, this is the hardest problem that I could possibly ask you guys, so I don't know what else to talk about for the next 12 minutes. Yes?
The other day in class, when we did this equation, VAN equals line current times impedance Y, why did we, instead of using the line current?
So, question that was just asked was the other day we had a circuit that looked something like this. So here's VAN. Here's ZW. Here is ZY. And we found this line current IAA. And I said that the voltage drop VAN could be determined by simply saying IAA times ZY. Today, we had this guy. Here's IAA. And we're solving for this VAN. And I used this current. And the reason why I used this current and not this current is because the line current splits up. Earlier, it didn't have any other paths, so the line current and the phase current were equal. Now they're not, so I used the correct one based on the circuit I had in front of me.